Recording in progress.
Okay, so let's get started. So I want to cover a few topics today in the double lecture. We'll start by looking at filters. There are actually many different ways of making it. And again, like many things, most of these analytic methods which are discussed in this book are not really used in practice because there are software tools for doing almost everything, where you just plug in your requirement and out comes the results. Even Microwave Office, the software which we have been using, has such tools in it. But we'll go through the basic ideas so that you understand what exactly is going on, at least for the few basic types of filters. And then in the second half, I will cover two topics. One is mixers. We have briefly touched upon mixers in some lecture, I think some time back. And then I'll end by talking about microwave frequency amplifiers and noise. How to think about noise, how an amplifier is characterized in terms of its noise performance. And that's sort of where we will conclude. There were a few other small things I wanted to cover, but I think we're running very late now, so I just want to wrap this up. So in terms of what's going to be there in the assignments and the final exam, this is basically the last lecture. I may send you some pre-recorded lectures just for your reference on some other topics, just for you to go through them at your own convenience. Okay, so let's start with this. This is section 8.3 in POSAR. And there's actually some preceding parts which talks about different techniques, but this is the one which is sort of most natural when you think about it. It seems to have a fancy name. It says filter designed by insertion loss method, but we'll see what that means. But if you look at the first sentence, basically it sort of defines what an ideal filter is like. It needs to have zero insertion loss in the pass band. So pass band is the range of frequencies where the filter allows the signal to propagate. Okay? Typically, your filter is a two-port device, okay, with an input and an output. But because it's a passive circuit, the input and the output doesn't matter. You can go from output to input. It's a reciprocal circuit. But once you put it in, you have a two-port network which has some frequency-dependent transmission properties. That's what you're mostly interested in. And what it says is the perfect filter will have zero insertion loss, which means the transmission coefficient is unity in the frequency range where you want the signal to propagate, and infinite attenuation in the stop band, which means that anything outside of the range of frequencies you're interested in doesn't propagate or go through at all. It's completely filtered by the filter. And then a linear phase response to avoid signal distortion in the pass band. Okay, so this is a slightly a subtle comment here, but which component has a linear phase response? Exactly, right? So we've looked at this transmission, what the phase of a transmission line is. It has a linearly evolving phase because the velocity of propagation, or the phase velocity, is the same at all frequencies. So just increasing for a finite length, different frequencies, higher the frequency, more the phase accumulation there is. So we know that an ideal transmission like that will propagate signals without distorting them. Distortion here basically means that if it treats different frequency components differently. Here we have already said that the magnitude of the response is the same in the pass band, right? Remember, the pass band is the region where we're interested in signal propagation. So that's what we're concerned about. So zero insertion loss basically means that it has the same response. Here, ideally, no loss, which means unity transmission. So the magnitude is constant across the band. And the phase has to have the same kind of a response like you would expect from a transmission line. It might not be what length of transmission line is up to us. I mean, it sort of depends on the design. But as long as it has a linear phase response, the signals which propagate through, they will all arrive at the end of the filter at the same time. So different frequency components don't get separated out. And then that means the output, if it's a complicated signal with many frequency components, at the output, you're not going to get something else. So this is also called dispersion, right? So you would ideally like this to be the case. All of these properties will be satisfied to some extent depending on the particular design you're using. Insertion loss, of course, depends on the materials you're using, whether the system itself is absorptive or not. But this kind of ideal response, it looks like if I now plot, let's say, transmission versus frequency, this looks like it's going to be something like this. Okay, so here I have drawn it for what we call as a band pass filter. So this is your pass band, and this is unity transmission. And then it has these abruptly sharp edges, and then everything transmission goes to zero, which means the same as infinite attenuation. Right? So this, of course, is not possible. At the most, you can have some kind of rounded response here, and maybe even the peak transmission need not be 1, depending on the loss. So this, of course, is band pass, but you can have low pass or high pass as well. Okay, so this is low pass, high pass. So this just tells you which frequencies are cut off and which frequencies are propagated. So low pass means it passes all frequencies below a certain cutoff frequency. High pass is the opposite of that. Band pass is, again, some range of frequencies it allows, which is not going down all the way to 0. And then you can also have something like this, which is called a band reject filter. Okay. So here you're only filtering out. So you're allowing everything to pass through except for a narrow range of frequencies. Okay. So here, when they say insertion loss method, they're essentially saying that I want to define transmission versus frequency. If you take the opposite of that, that's the insertion loss, right? So how much loss it is getting to go from one port to the other. If you define that as a function of frequency, that defines your filter. So here we're going to choose certain nominal shapes for this frequency response and try to construct circuits which will give you that particular response. Okay. So they've also defined this other thing called power loss ratio, which is another way of calling the insertion loss. And the insertion loss is sort of defined in dB as just the 10 log of the power loss. Basically, it's the same thing, just in dB. So what is the definition? It's power available from source divided by power delivered to the load. So this is just another way of talking about it, but they now relate it to the reflection coefficient mod square, right? Because the power delivered to load is 1 minus the power which is reflected. So gamma square, so gamma is a reflection coefficient, remember? And mod gamma square is the power which is reflected. So 1 minus that is the power which is actually delivered to the load. So here, so if this is your filter, we are talking about source and then load here. So this is all, ideally this is all 50 ohms, okay, everything. And this is your source. So we're talking about the power delivered here versus the power that is actually available, which is essentially the power which would be delivered to the 50 ohms if there was no filter in there. So you go from insertion loss now to a reflection coefficient, and then we know some properties about the reflection coefficient. So we can define some kind of a function to represent this, which is going to follow one of these kind of patterns. Okay. And that idea is that mod of gamma square, when we were looking at reflection coefficient and S matrix, we saw these even odd properties of the impedance and reflection coefficients. So mod gamma square is always an even function of omega. So that means you can write it down as a polynomial in omega square. And they choose this particular form for gamma square. This is kind of arbitrary in some sense, but you choose this form so that the insertion loss looks like this, which has a simple form which can be mapped to a few different kinds of responses, which is what we're going to see now. Okay, so now we are just defining some generic mathematical shape, which hopefully we can realize using some circuits in a simple form. Okay. So the first and the most commonly used one is what is called the maximally flat filter. And it's also called binomial filter or Butterworth filter. So this response function is called a binomial response or a Butterworth response. And that function is given here in 8.53. So it's saying that power loss ratio is 1 plus some constant k square into omega over omega c to the power 2 to the n. Okay. So just to note this is, if omega goes to 0, the power loss ratio is 1. Okay, so this basically automatically tells you that this is a low pass filter response, because at low frequency, the power loss ratio is 1. So 1 here basically means maximum transmission, right? And then it falls off as omega increases with respect to omega c. And it's 2 to the power n. I'll just talk about the 2 now. The 2 is there because we have restricted this to these even powers of this even function of omega, right? So at the minimum, omega is omega or omega c. If n is 1, you're going to have this factor of 2 there, square. Now, let's just look at this function a little bit more carefully and identify some other points, right? So one was that power loss ratio at omega equal to 0 is 1. And it's clear that as omega increases, this power loss ratio is going to become smaller and smaller. Sorry, it's going to become larger and larger. This is the loss ratio. So loss is going to increase as omega becomes larger. If you want the power loss ratio to have some value at this frequency omega c, this omega c is actually now the special frequency which defines something about the filter, right? Which is usually called as the cutoff frequency. And it's standard for most filters, or whenever we define bandwidth in microwave circuits, is to use the half power point, which is also called the 3 dB point, because 3 dBs is basically a factor of 2 in log units. Sorry, it's 3 dB in log units, it's a factor of 2 in linear units for the power, right? So if at omega equal to omega c, this is going to be 1, this coefficient here. Doesn't matter what the power is here, that will still be 1. So then if you want the power loss ratio to be double of what it was, because that is same as transmitting half of it, then this k square has to be 1. Okay. So this basically k square sort of helps you define what is the power loss ratio at the cutoff frequency. So remember, if we go back to these generic responses, this filter response is basically characterized by a few important things, right? One is, when does it start to fall, right? And this cutoff frequency is basically a reference of that. And then the question is how fast it falls. So it could have, fallen like that. It could have fallen like this. That is what the other point is. And of course, at low frequencies, it should have unity transmission. So this other quantity, which is this power 2 to the n, that basically determines how quickly the loss is going to increase once you cross the cutoff frequency. So this basically tells you how effectively, or what is the range of frequencies it's going to start rejecting from the range of frequencies, which is, yeah, this does that sometimes. Okay. So typically, because we use the 3 dB point as the definition, k square is essentially going to be always 1 for most of these filters we look at. This power n is also called the order of the filter. The larger the n, the faster the loss will increase as frequency increases. Right? That's obvious, because once omega crosses omega c, then basically depending on whether it's 2, 4, or 8, this function will increase a lot more rapidly as n increases. Okay, so this sort of simplest shape determines this kind of response. And the part of it being maximally flat basically means that now this flat part is related to the response in the pass band, which means within the range of frequencies you are interested in transmitting, can you actually keep the transmission constant across the whole band? Right? Again, that is not something which is possible to do perfectly, that you cannot have exactly the same amplitude. I'm not even talking about small errors due to some, imperfections in the design. Fundamentally, it's not possible to have it to be exactly flat and then suddenly start to change. So this kind of a function gives a very slow, sorry. So it gives a very slow change till you reach this omega c. Okay. I'm used to drawing these curves the way one sees these responses, but if you actually think about it, it might not be like this. I'm sort of drawing it in the log space. Okay. Because this is basically like a parabola, right?
Actually, the response is increasing, right? I mean, PLR.
Sorry, I'm plotting the one minus that. Or what am I plotting? Basically, yeah, I'm plotting the transmission rather than the insertion loss. So this part is slightly confusing because I don't know. To me, it's natural to talk about the transmission versus frequency, but what they're defining is the one minus that. Okay, so which is what they're calling as the insertion loss here. So you're right. This function here actually will be 1, and then it will go like this. So 1 minus that will do the. It's actually not even 1 minus that, because this is a ratio. Because 1 minus thing will give you a 0 at the origin. Right? Okay. But that's just the way to character. You can characterize it equivalently. Here, the functional forms are defined with respect to this quantity, which is called as the power loss ratio, which we defined here. Okay. This quantity here. So if I, in fact, we can see the exact definition, right? So gamma square is the reflected power. 1 minus gamma square is the transmitted power. Here we are assuming that there is no other type of loss in the circuit which absorbs energy. So then this is basically 1 over the transmitted power. That's what the power loss ratio. So it's not 1 minus, it's 1 over. So in log units, it's minus. So that's what it is. Okay. So this is one type of a filter response, which is again the most commonly used filter response, because it makes sense. It has a fairly smooth flat band, and then it drops off in a particular way. You can control where that drop off is going to happen by controlling omega c. Then you can change n to get how fast it falls off once you pass the cutoff frequency. So remember that the power loss ratio will go from 1 to 2 from 0 frequency up to the cutoff frequency. and then it will start to rise quite rapidly. There is also another type of response which is used. I've never seen it like actually a filter which we purchase which will have this kind of a response. I guess it's it must be for very specific reasons. And this has a very similar response function except for this extra factor here, Tn. And this is called an equiripple or a Chebyshev filter. Okay, so this Tn is basically this Chebyshev polynomial, which has an oscillation between plus or minus 1 for, so Tn of x oscillates between plus or minus 1 for x, this is I think missing, mod x square less than 1. So the insertion loss here, so you see that this part here outside of the Tn has the same function as this guy. But now in addition to that, instead of just being this smooth, so here the maximally flat is plotted here. So this one is the maximally flat. So that's the 1 plus omega or omega c to the power 2 to the n. And this is the equiripple one, which means that in the pass band, you get this kind of oscillatory behavior. So you see insertion loss, instead of varying smoothly and going up to this value 1 plus k square, which for most of us will be 2, oscillates between 1 and 2. In this case, there's one period of oscillation, but that basically depends on the the order one is using. So the order of the Chebyshev polynomial you're using. So it's called equiripple because these ripples, which is basically the small changes in the amplitude, are always of the same magnitude. They go from 1 to 1 plus k square. Okay, because Tn goes from plus minus 1. This is a different, how should I say it? A different optimization where you say that, okay, I can tolerate some variation in my pass band. So remember that even in the other case, there is some variation. It goes from 1 to 2. It's not a perfectly flat situation. So here you're allowing, and of course, the magnitude of this is going to depend on the value of k you choose. You could choose a k which is different if you like. That you say that, okay, I'm going to now tolerate some variation in this kind of periodic as long as the maximum variation doesn't change, and that you constrain by the filter design. But you get an extra advantage that after the cutoff frequency, the power loss ratio increases typically faster compared to the same maximally flat filter. So you see this part here is rising faster compared to this one, which means the filter has a much sharper cutoff. So this is important if you want to reject some frequencies which are very close to frequencies you actually want to pass through. But you say that, okay, the price you pay is this kind of a ripple. Okay. So this is another optimization you could do to construct filters. And as I said, this is not used that commonly, but this also allows for designs which are straightforward to construct. And then there are actually several more. So here is another one which is called the elliptic function, where you have ripples both in the pass band and in the reject band. Here the constraint is that you guarantee that there will be at least this much of insertion loss. So this is again a different optimization where you say that I want my filter to at least reject by a factor of 10 or a factor of 20 between the pass band and the reject band. And then there are some frequencies where the rejection is much better, but the worst rejection is at least at this value. Okay, so this is another optimization called the elliptic design. Again, in practice, I've never really seen this being used. Okay, so the thing we are going to look at in more detail is this simple one, which is the maximally flat design. Okay. We'll also see how the Chebyshev one looks like. Any questions so far? This is, I mean, very basic stuff. So now you try to construct a prototype of a circuit which may give a response like this. Okay, I mean, it's not obvious just from looking at it that one is going to get a response like this, but it you know that you need to use inductors and capacitors, right? Pretty much that is the only two components you have. So here is a example circuit where you have your source. The source impedance is given at a value 1 because it's just a mathematical simplification that you normalize everything to 1, and then you do the calculation, and then after that you can use some scaling equations to put them to any impedance you like, and similarly any frequencies you like. So you scale the impedances to 1, and you scale the cutoff frequency also to 1. So the omega c is always 1, and then later on this 1 can be moved to wherever you want. So we'll see that in just a little bit. So you have your source. So remember, this is your source. This is your load. And this here is your filter. Okay. Looks very simple. In fact, you have seen these kind of filters in electronics courses, even in maybe undergraduate classes. You have probably seen a different versions of this, which is the RC filter. And the idea is basically exactly the same. If you look at, if you have some V in here, I'm just sort of now thinking purely in terms of voltages, we're not worrying about the impedance, then V out over V in can be just done by a voltage divider, which is basically X of C over X of C plus R, right? And we know that as frequency increases, this capacitor's impedance is going to become close to 0. So the voltage drop here, V out, is going to go to 0 at high frequencies. At very low frequencies, this is going to look like an open. So V out will look equal to V in. So this sort of also has some response like this, right? Now, this of course uses a resistor here, which we don't want because we don't want the filter necessarily to absorb power as well. But the same function can be obtained if you put an inductor here as well. In fact, that sort of doubles the effect, because now the capacitor going to 0 impedance is also there, but the inductance is also increasing in impedance, right, as we go to higher and higher frequencies. So this ratio, which is going to be now XC over XC plus XL, this will again go to 0, in fact, slightly faster. And this also has the same kind of response, which means good transmission at low frequencies and smaller transmissions at higher frequencies. So the simplest low-pass filter, which is made of only non-dissipative components, is going to look like this. And you might have thought that maybe this N equal to 2 looks strange here, but it's basically because both L's and C's are frequency dependent. So the simplest filter here is going to be of order 2. Okay. And that is the insertion loss function we are going to use. So we have used K square equal to 1. So remember that power loss ratio was 1 plus K square omega over omega C to the power 2n. So we've used K equal to 1, which just gives you a 3 dB cutoff at the rejection at the cutoff frequency. And omega C is also been set to 1 and n is set to 2. So that's what we get. So K equals 1, omega C equals 1, and n equals to 2 gives you 1 plus omega square. So that's the function we are trying to construct. And if you know power loss ratio, from that you can use the previous relation to get the gamma, because power loss ratio was 1 over 1 minus gamma square, right? Let's just double check that. Yeah, 1 over 1 minus mod gamma square. So you have defined now a functional form for PLR. From that, you can get a functional form for gamma or vice versa. And then how do you get gamma? Gamma is just your z minus z naught over z plus z naught, because everything is normalized to 1 here. That's why you have this function here. And what is z in? Z in is basically the input impedance seen at this point. Right? So it has the filter and the load resistor included in this, because we are talking about with respect to the source. So everything else is now part of the input impedance, which we use for computing the reflection coefficient. So you can basically do that for the simple LC circuit, which is what they do here. I mean, the math is messy, but it's straightforward. And you get basically an expression for PLR in terms of this L, C, and R. Okay. And you see it's a fourth order polynomial equation in omega. Now we want this to look like, because we want PLR to be 1 plus omega to the power fourth. This is the function we're trying to implement. So you now try to identify features here which would give you that. So we need R equal to 1. And we want this part, which is basically the coefficient of omega square, to go to 0. Okay. Now, R equal to 1 should have been obvious from before, because we have started with a source impedance of 1. And this is a match system. Okay. So in fact, it's saying that only for such a match system can you create this kind of a filter response that easily. And because you also want this, PLR equals 1 for omega equal to 0. That's where the R equal to 1 comes from. That's just the matching condition. And then you want the coefficient of omega square in this equation, which is this one, going to 0 as well. And that, when you solve, gives rise to a value of LNC equal to root 2. So remember, all of these are normalized, right? So this root 2 what? Okay, doesn't have any units right now. It's all dimensionless. So we have to do the scaling thing. But this condition will allow you to construct this kind of a response. Okay. Now, then if you want to make, so what have we chosen here? We have chosen a cutoff frequency of 1, and we have chosen an order of 2, which gives you this power loss ratio going as omega to the power fourth. So typically, if you want now to improve the filter, or in the sense that you want the same cutoff frequency, but you want a sharper response, you have to go to higher order. Higher order basically means you need more LC sections. That is what is going to give you a faster change in the response. So this method gives you a generic way of constructing these filters, which is basically a network of L's and C's like this. So parallel, so shunting values with C and series with L. And you can, in principle, try to compute Z in and figure out what the values of L's and C's, but that will become very messy. So people, now you can do it on a computer, but earlier also they used to basically create tables for this. So it forms a particular pattern where you have tables which gives you values of these constants G0, G1, G2, G3. So G0 is always the value of the source impedance. So that gets fixed when you do the scaling. And then the last value is the load, which again, in most typical cases will be equal to G0. And then you have these G1, G2, G3, which gives you the values of the capacitance and inductance. So one gets a table like this, which allows you to now construct. So these are for maximally flat low-pass filters with G0 equal to 1, omega C equal to 1, and N going from 1 to 10. So just from this table, if you want to construct, you can basically pick which order, and then that gives you these numbers. And from that, you can calculate the value of your L's and C's you need to build the actual circuit. Okay. So this kind of tables used to be created basically from a computer program which would solve those equations for you so that you don't have to do it every time. So why this is standard is that because we have normalized everything, you can now scale this to any frequency and any impedance. Now, of course, that impedance is almost always 50 ohms for most microwave circuits. But if you are building something custom, you can do that as well. And you can just look at this and do the scaling. So where does the scaling type come from? Let's a little bit over here. Oops. So this is basically what allows you to compute the actual values of L's and C's you need. Okay. So these L's without the primes are the ones you calculated from that table for a given filter design, which basically means the only thing you specify is the order of the filter. And then you get the circuit and the corresponding values. And then you scale everything by the value of the source resistance, which is basically 50 ohms. So L prime becomes 50 times that. And remember that this is still, the units are a bit strange because this is all in terms of impedances, because the frequency part is still written as 1. So that will come next, but this is one step of the scaling. And then you do the scaling by setting omega by omega c, whatever the actual omega c value you want, and then you get these equations. Okay. So remember that this will now give you the correct units for the inductance and the capacitance. So it went from dimensionless into something which looks like an impedance, and then you scale it by frequency to get you an inductance. And same way for the capacitor. So you now have the full methodology for starting from the order. You're constructing a low-pass filter, you look at the table, you get your values of these scaled L's and C's, and then you scale them to the correct frequency. And then that basically gives you the correct values of the inductance and capacitance in default units. And then you get your frequency response you like. And you can sort of understand this, that the shape is fairly standard, right? All that's you're moving when you're doing frequency scaling is sort of moving the x-axis back and forth, but the generic response is always the same, which also means that the how fast the filter function falls off is actually related. If you say that it's going to fall off by this much factor over this range of frequency, that range of frequencies you should correctly define as a multiple of the cutoff frequency rather than absolute frequencies. Because remember, this is all scaled with respect to omega c. What I'm trying to say is that if you had a 1 gigahertz cutoff filter, and you saw that from 1 to 2 gigahertz, the attenuation increased by a certain factor, if you now scale this to a 10 gigahertz filter, that same attenuation factor will not happen from 10 to 11. Okay, it will happen from between 10 to 20 because it's the difference between the ratios of the frequency. So 1 to 2 is a factor of 2. So when you scale the whole thing to 10 gigahertz, that will be the fall you will get as you go from 10 to 20 gigahertz. So it's all ratiometric. You have to keep that in mind when you construct your things, which basically means that if you go to higher frequencies, you need to have higher order filters to get a very sharp response in your filter function. Okay. So there is also other things which I'm not going to go through, and you can take a look at it, is that the same method with some simple transformations allows you to construct high pass filters, band pass filters, and band reject filters. It just requires you to do some further scaling. And the generic circuits start to look like this. So yeah.
So the ratiometry is the log scale itself and not the linear.
No, it's all, everything is in the linear scale.
So that, if it's ratiometric in the linear scale, then 1 to 2 should go from 10 to 11. The log scale.
but I'm not comparing between linear and log scale, right? What I'm trying to say is that the your function goes like this, right? So omega or omega c, once you fix n, the how much insertion loss you're going to get at a particular frequency omega is going to depend on how much omega is with respect to omega c, right? So for example, if you had n equals 2 and you had 4, so at omega equal to 1, insertion loss is 2, right? And then if we go from omega equal to, omega or omega c equal to 1, if I now go omega or omega c equal to 2, then it will be 1 plus 2 to the power 4, which is going to be 17, right? But if omega c is 1 gigahertz, then omega for this point is 1 gigahertz and for this point is 2 gigahertz. So in 1 gigahertz, it went from 2 to 17. But if omega c was 10, then this point is 10 gigahertz, but this point is 20 gigahertz, right? So it actually gets stretched out. The filter response gets stretched out as you go to higher and higher frequencies. So absolute frequency differences will not give you the same attenuation factor. So that's why often these things are, even when we talk about, this kind of stuff is often called filter roll-off, right? How fast the attenuation increases. It's often given in, it'll say like dB per octave. Okay, octave, the language comes from actually music, because as you go from one octave to the next octave, so I don't know for the musicians here, if you go from sa to the next higher sa, the frequency gets doubled. So that is, so an octave in frequency means a doubling of frequency. And you basically say that if you double the frequency, the loss will increase by a certain amount. Or in log units, you'll say dBs per octave. You'll say 10 dB per octave. That means that every time you double the frequency, the loss will increase by 10 dB. Okay. So if you look at it in an x-axis, which is a linear frequency scale, you will see that the 1 gigahertz filter will look sharper, just because it falls rapidly over 1 gigahertz. But that same drop will happen over 10 gigahertz at when you have the cutoff frequency as 10. So that's what I was trying to say. Is that clear? Yeah. So this table basically then tells you that same generic structure. Now, what is, let me just go back. What is the generic structure I'm talking about? I'm talking about this network here, right? Which had the, so this network of shunt Cs and series Ls, again, you can have, depending on the order, you can have many of them. If you just take the same structure and basically consider that these inductors and capacitors are some elements, not necessarily only inductors and capacitors, but could be anything generic, then this table here, which we were looking at just a little while ago, basically tells you another set of transformations which allows you to construct different types of filters in the same model by just changing what those elements are, right? So in the low pass filter, you had L's going like this and C's going like this, right? So that's what this first part is representing. You have L and C. If you wanted to use the same thing, but construct a high pass filter, then you just interchange the inductors and the capacitors, right? That's obvious from construction when we looked at how the LC circuit filters. If I now put the inductor down and the capacitor here, then the condition we saw for very low frequency becomes the condition for the very high frequency. Because at very high frequency, the series capacitor is going to be a short, and the parallel inductor is going to be an open circuit. So it's as if that circuit was not even there, right? It's like the two parts are connected. So you get unit transmission at very high frequencies and no transmission at essentially zero frequency. So the fact that low pass becomes, by just changing L's and C's becomes a high pass filter is kind of natural to see. But you have to do this scaling to get the values correctly. Because remember that you calculated the L from that table. But now to get the equivalent C for the high pass, you have to do this transformation, which is written here. Similarly, you can replace each of those elements with either a series LC circuit or a parallel LC circuit. So this means that you're going to put series LC instead of the L and a parallel LC instead of the C. And that turns that into a band pass filter. Right? Again, why is that? If you look at the simplest response, which is going to now look like this, right? This is going to be the n equal to 2 case. I've changed the L into a LC series and the C into a LC parallel. If you look at it from, again, the point of view of the extreme points, but here it's a band pass filter. So it's going to have maximum transmission at some special frequency. And that's obvious to see that if these two LC circuits had the same resonant frequency, then at that resonant frequency, the LC circuit has zero impedance, series one, and the parallel LC has infinite impedance. So that is equivalent to saying that this point is essentially connected to this point and this doesn't play a role. So you can see it will have maximum transmission at the special frequency corresponding to these LC circuits. And if you go on either side, you will get only less response. Right? It can only go down. So this tells you again just intuitively why this is a band pass filter. And the same thing you do that if you now want a band stop, where you do the opposite. So you put a parallel LC here and a series LC. So that means at resonance, it shorts the point and also gives you infinite impedance. So it's completely disconnected at the special resonant frequency. And then everywhere else, it will only become better. So this one will have, a response like this. This one will have a response like that. This will have like this, and this will have like that. Right? So you can see how the same simple model can be extended, and they give you all the scaling factors here. So the delta for the band pass, it's a little bit more complicated. You can read through that, but this delta is basically related to the difference in the frequencies, because now for band pass and band reject, you have two frequencies to determine, right? The left edge and the right edge, or equivalently, you can also define it with the center frequency and the bandwidth. So it can be defined either in terms of omega naught and delta, or omega 1 and omega 2. Right? So just using these transformations and those tables, you can construct all these 4 generic type of filters to whatever order you like. Okay. I'll just quickly mention this other part. So there was a table for your maximally flat filters, but you can also do the same thing, a similar analysis for your equiripple type of filters as well. And there's a different table for that. So here you have a table for 0.5 dB ripple. So this is basically how much you allow it to vary. And then a table for 3 dB ripple. And then you can go and construct the filter. By the way, the model is still the same. You just, again, it's a network of L's and C's, but now by choosing different values of L's and C's, you can get either the maximally flat response, or you can get this Chebyshev equiripple response. Okay. Let me just quickly show you one more thing, and then we will look at the some examples in microwave office. So all of this was again in terms of L's and C's. And as we have discussed over and over again, might not always be possible to get ideal L's and C's at microwave frequencies. So again, you can do some mapping and construct these filters using sections of transmission line. So here, I'm not actually going to go through detail, just going to show the basic idea here, is that there are some transformations which allow you to identify, and we have sort of done this earlier also when we looked at modeling how a resonator looks like a parallel LC circuit. We try to see how to get the equivalent thing. Similarly, just an inductor or a capacitor can be thought of as sections of transmission lines with different boundary conditions. So a short circuit, a section of transmission line which is lambda by 8 at omega c. So remember here, the frequency of cutoff plays an important role, because these transmission lines are always going to behave like your lumped element over a certain range of frequencies. So the natural frequency for these filter designs is always the cutoff frequency. Basically, in the range, you want these to behave the way you are trying to model them. So you can have a short-circuited section to replace an L, or an open-circuited section to replace a C. And by then using the same model we just saw and replacing those L's and C's with these sections of transmission line, you can actually construct filters with these sections. And the difference is going to be that these filters will only function locally in that frequency. So it's kind of a bit strange, because it's not ideal in that sense, because you like a low-pass filter to transmit up to some cutoff frequency and then never transmit again, right? But if you construct it using a transmission line-based idea, at some point, it's not going to work. So usually what you will see is periodic response. So if you don't particularly care in certain applications, you might say that, okay, I want to pass between 0 and 1 gigahertz. I want to reject everything between 1 and 5. But I don't particularly care what happens after 5 gigahertz, then this kind of circuits are okay. Otherwise, you will never get the same ideal response we got, because the transmission line is going to have periodic properties as you go to higher and higher frequencies. So the response will repeat. So you can never get this whole thing by just copying exactly the same methodology. So that is one thing you have to keep in mind. For band pass filters, also it's the same idea, but there at least you might have a better chance, because usually you're only interested in the frequencies around the operating frequencies and not necessarily far away. So this is something you have to keep in mind when you construct filters out of transmission lines. And basically they start looking something like this. No, that you can construct, because basically there is a mapping between the value of L's and C's you need to the particular transmission line you're going to construct, right? Essentially, it's going to be the characteristic impedance of the transmission line, right? That's the only thing you have. You have two things you can control with the transmission line: the length and the characteristic impedance, and maybe the boundary condition. Okay, three things. So once you make the mapping, if you do it for equiripple, then you'll get the equiripple response but only in that specified band of operation. You will see that it'll reproduce. It will repeat again in the same way later on. So here's an example of what these filters might look like. So here you have the lumped element version in the part A, and then you see that this L here has been replaced by this shorter section of transmission line. Same for this one. And then the C has been replaced by this open-ended transmission line like this. Okay. So this is the equivalent circuit for that. And you can have more sections, and that will give you, and the thing is, these kind of things are possible to do very easily in a microstrip geometry, right? So this is a microstrip geometry design shown here. So these are your feed lines, 50 ohms coming in, and then the filter starts, right? There is a parallel section. So this is an open end here. So this is representing some capacitance to ground. This is playing the role of a capacitance to ground. Then this is playing the role of the inductor. Again, inductor, capacitor, and capacitor. Right? So one thing you notice here is that these sections of transmission line which are playing the role of the inductor have a high characteristic impedance, right? And that kind of makes sense because Z naught is this, right? So you're trying to get more inductance. So you want to have high impedance transmission lines. And that's why it's narrow here. And the opposite for the things you're trying to build capacitors with. They will typically have low characteristic impedance. Then one also has to worry about whether these numbers, the characteristic impedance of 200 ohms or 60 ohms, are these practical? Because remember, again, you cannot make very high or very low impedance transmission lines in the conventional geometry. Okay. So this is actually the one that I have. So this, you see that it can actually be constructed quite easily, but the price you pay is that you have some periodic response. So it will, a low pass filter particularly will not work after some frequencies. It will again have a transmission.
You said that the transmission lines of 25 to maximum.
Yes. Yeah, this one is just, this is just a calculation example. You can make it, it will just not probably radiate a lot. Somewhere, when I was preparing for the lecture, I saw that Ozar says the range is between 20 ohms and 120 ohms is sort of the typical. So see, these practical dimensions are somewhat dependent on the exact nature of the circuit board itself. We talked about two reasons, right? One is that when you want to make very low characteristic impedance, then the size of your transmission line is going to get bigger because you're trying to increase the capacitance per unit length. So if you consider the microstrip geometry, then the capacitance per unit length basically comes from how big this, because this looks like a parallel plate capacitor, right? So if it gets very big, and especially if it becomes the size or comparable to the wavelength but now in the orthogonal direction, right? In the width of the microstrip starts to become comparable wavelength, then you have to worry about the fact that there is actually a phase change from one end to another. So that's the non-ideality that kicks in. But what sets that size? It's actually related to the height of the dielectric and the dielectric constant itself, right? So it is possible to imagine a scenario where you have a very, very thin circuit board, so very thin dielectric and a very high dielectric constant, in which case it will be possible to construct smaller circuits as well. So you can it will be possible to construct low impedance transmission lines which are not very large. Now, this is also not a perfect solution because as you go to high capacitance per unit length, the velocity of propagation also slows down, which means the wavelength also becomes smaller. So what is considered small also changes, right? So it's not a simple compromise, but it is possible to make, maybe a 10 ohm transmission line if you really like. But for the standard circuit boards, which one uses for standard thickness and standard dielectric constant, it becomes difficult to go below 20 or above say 120. And on the other side, on the high impedance, if it becomes like a very narrow piece of wire, then it just sort of stops seeing the ground, and then you can have radiation into free space. So that's the other side why you cannot go to very high impedance. But it is possible to construct, use special materials. Now, this might not be possible to do with copper or gold-plated copper for conventional circuits, but using superconductors, you can actually construct transmission lines which have much higher impedance, because they use another type of inductance called kinetic inductance, which doesn't depend on the geometry. So you can get more inductance per unit length than you would get for a geometric circuit you are making. But that's a completely specialized type of things. So that's what constrains these things. So yeah. Essentially, the capacitance to the ground becomes very small. So let me try to qualify that a little bit better. So it's basically saying, why is the wave confined to this transmission line, right? as opposed to just an open wire. It's because of the presence of the two conductors. But the fact that you have free space and electromagnetic waves can propagate is basically this. If this confinement doesn't happen very well, then you will get radiation into and that becomes worse as you make the lines smaller and smaller. It's not contained in the simple model, right? The LC ladder network is going to be always going to give you the perfect transmission line equation, irrespective of the value of L's and C. But that's an approximation. The problem is that when you're sort of ignoring the fact that there is free space around it when you're saying that all the electric fields are confined between the points of the transmission line, with just some spread around it. But if you just have a piece of very thin piece of wire, then it can actually start to radiate into free space. Okay. So this is one type of things. And again, you can do the, so here's, for example, we're just showing you that the distributed element thing for a low pass filter, for a lumped element, it keeps going down. And then for the distributed element, actually comes back up. So it's this now, I don't know whether you would call it a low pass filter or a band reject filter, right? Because it looks like it's passing here and rejecting everything here. So it all depends on whether you care about this frequency to the right of this or not. If you don't care, then it's a low pass filter for your purpose. But if there are things in the experiment or in your system, there are frequencies here which should not pass through, then this is no longer a good filter. But you could, for example, cascade filters having different cutoff frequencies to give you an effective response which is more suitable for your case, and that you can still construct with transmission lines as well. But that becomes more and more complicated. Okay. And then just one last type of filter I wanted to mention is, because these are again things which can be constructed easily, are these stepped impedance low pass filter. And I have an example of that here. And this is basically another way of constructing or replacing L's and C's with sections of transmission line. And this again is just an idea that a very small section of high impedance transmission line looks like an inductor, and a very small section of a very low impedance transmission line looks like a capacitor. But remember, it's not a capacitor, or the direction matters. So this is representing a short section of a transmission line, right? So you have LC, 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 and you're just saying, okay, I'm just looking at this very small section, so I can model it like this. But if the characteristic impedance was very high, I can basically ignore the capacitance part and only draw it like a series inductor. And vice versa, if I have very high capacitance, which means low impedance, then I can ignore the inductive path and consider that as a capacitor. So this is slightly different than the previous argument. Here, it's just a section of transmission line, again, going from left to right. If it's high impedance, it looks like a series inductor. If it is low impedance, it looks like a parallel capacitor. So, and basically that's what you want for a LC, for a low pass filter, right? It's LC, LC like that. So the advantage here is that you can basically just have two values of transmission lines, two values of characteristic impedance of transmission lines, one low and one high. And then you can construct basically something which you start from here and you replace all the inductances with a high impedance transmission line section and all the capacitance with the low transmission line section. But because the value of L and C is changing, the lengths of these sections is going to depend on that. It's still the same model. You construct something, you calculate, you put the cutoff frequency, find the values of L's and C's. And now there is a mapping which allows you to just create a series of transmission like this. You fix the choice of what you're going to use for the low and what is going to be used for the high, right? You might say, well, why fix it? Because you actually want the largest impedance possible for the inductance and the smallest impedance possible for the capacitance. And then you just choose the length. So the table, which was earlier giving you L's and C's, will now get transformed to basically giving you length of low impedance line, length of high impedance line, length of low impedance line, and so on. So, and then you can construct this kind of, and this is called a stepped impedance filter. And you can see that in microstrip again is very easy. It's just changing the widths of the thing. So here is actually a filter made like that. You can take a look, pass it along, hold it from the middle. Okay, don't hold it with the connectors. I think this is a 5 gigahertz, 5.5 gigahertz low pass filter. Yes, so that's the cutoff frequency, and that's always the 3 dB cutoff frequencies. Typically, that's how you define it. Okay. So we'll just look at the simple single LC section filter response, and I'll just point out a few things. Let's see if I can use one of the examples here too. Is this not? example for the simple thing, but I will, for the case of just one LC section, I want to look at it in a slightly different way, right? So you have essentially only two parameters, which is L and C. But remember, we have talked about parameterizing this in terms of two other quantities, which is actually the resonant frequency and the characteristic impedance, right? The ratio of L to C. This is not a transmission line, but it's an LC section. So we can also basically say it's either the product of LC and ratio of LC. So you can see that the resonant frequency part will be related to where the cutoff frequency is, right? But the ratio of L to C, which is the characteristic impedance part, will do something else. So I want to rewrite this in terms of those parameters so that we can see how that gives you the type of response we have been aiming for. So let me see what this plot looks like in the first place. Okay. Some filter. This is in dB units. Let me plot it in linear units. So you have unity transmission. So I'm plotting S21 mod, right? So you have unity magnitude transmission at very low frequencies, and then it falls off. And the thing we have to look at is the point where the, okay, this actually would be, sorry, this is linear magnitude. Right. Okay. I guess it's no simple way to plot the power. So let's do this thing. I think I've shown you this output equation part as well. So I'm going to define a variable which is S21 mag. Yeah. And I'll define S21 max square as S21 mag. I'll just plot that now. So the half point is somewhere around here. It's saying 6.3 gigahertz. Okay. So I'm going to redefine these L's and C's in terms of omega and Z naught. Okay. So I'm going to define F naught, and I will call that in gigahertz 6. Then I'll define omega naught as 2 into 4 into F naught. Oops. 1E9. Define Z naught, let's say 10 ohms to start with. And then I can never remember this. So let's see. So C filter is going to be 1/0 into Z0. And this is going to be in farads. I want in microfarads, so I multiply by 6. And so L filter is going to be Z0 omega naught. We also print the values here and left. So this is need this in nanohenry, so 1. Does this look right? 1/Z0 omega L. Inductance 0.2. Okay, so some. Sorry, just 1 second. Sorry, that was my dentist. Okay. See if this is something. Right. Can you just check if I made a mistake? So I've defined 6 gigahertz. So 2 pi f into 1e9. Z0 is 10. CF is 1/omega0 C0 into 10 to the power 6. Right, this is a microfarad. Somehow I feel the capacitance value is too small. Yes, this is 210 minus 1. Hmm? YZ. No, units bytes is okay, right? So impedance of capacitance goes as 1 over omega C. So C will be 1 over omega into Z naught. That's fine. But wait a second. So no, it's okay. This is 2.6 10 minus 10 henries, and this is 2.6 10 minus 6 farad. So ratio of that is 100, square root of that is 10. So this is okay. No, I've just, to keep it simple, I've defined this in gigahertz, but I've used the 1E9. No, this is okay. It's okay. It's okay. But this is basically what I want to show you, that the cutoff frequency of is not really the same as the LC resonant frequency. It's, remember that when we're doing the dimensionless case, we got L and C as √2, right? So let's look at that part here again. Yeah. See, if L and C is √2, then omega, which is 1 over square root of LC, is 1 over square root of √2 into √2 is 2. So it's 1 over √2, right? It's not the same frequency as what your LC would be like. Because here the cutoff frequency is at 1. See, here omega C is 1, but omega is 1 over, omega resonance is 1 over √2. Which means that, so omega C is 1, omega resonance is 1 over √2, which means omega C is √2 into omega resonance. So, no, wait. No, sorry. It's over √2. Yes. That means cutoff frequency is going to be √2 times the resonant frequency of the circuit. So we'll now put tuners on this. Basically, these are the only two things I can control. And let's see what happens to this shape of this curve. First, I'm going to tune the resonant frequency. Okay. So the point where it crosses 0.5 is changing, right? But the same thing will also happen with this guy as well. So, say I choose some value here, and I guess there is a L over C is also fixed, right? Because of this design. L over C here is always going to be 1. So Z naught of 1 also basically means if in this dimensional regime L over C is 1, so square root of that is also 1. In our circuit, what would that be? the scaling is basically with respect to 50 ohms, right? So I think the thing you need is that this has to be always 50 ohms. So now you see the curve starts to look the way we were seeing it before. Like it has this flattish response and then it falls up to 0.5. Let's, I don't know why it chooses some really weird division here. Divisions. Oh, I guess it's because of somebody else is using. Who's this? This is Anirban. Huh? Second. Okay, I guess it doesn't matter. We can choose whatever frequencies. So now this point at power ratio of half is around 6.09 gigahertz. And the cutoff, the resonant frequency we have chosen is 4.29, right? So if I, oops. If I take that ratio, so I said that omega resonance is omega cutoff by √2. So 6.09 divided by 1.414 is 4.3, right? So 4.29. So that's what basically this is. So in order to get the idealized performance, you have to keep the ratio of L to C always as 50 ohms. Only then you will get this 1 plus omega square, 1 plus omega to the power 4th kind of response. Now we can just move this frequency and then you can sort of see this. It's the same thing which is just stretching out now. So see, this is sort of the scaling effect, right? I'm just keeping everything else the same. Everything else meaning the characteristic impedance of L to C is the same. Let's look at over a larger range of frequencies. In fact, let's do something better. Let's actually define the cutoff frequency here. F cutoff gigahertz is 5. And cutoff, so resonance is cutoff divided by √2, right? So let's see. So now I can just tune the cutoff frequency, which is easier to read off from the resonance. Yeah. So cutoff is at 5 now, and you see that at 5 gigahertz, it's exactly half, right? So this is the point I was making earlier, and when Aishi, you were also asking, you see that it looks less sharp as we go to higher and higher frequencies because everything gets stretched out. As I come to lower and lower frequencies, then this range is smaller because it's all multiple of that. And these filters also have a sort of a characteristic shape in log. Sorry, I can't use this one now. Let me go to standard port parameters. Nice. I'm going to make the x-axis log scale. So this is now the same filter response in log scale, right? The y-axis is dB. The x-axis has been changed to log scale. So this is now a very characteristic shape in this log scale that you see a flat response and then basically a linear fall off, right? So this looks like so there's a straight line here, and then there's a straight line here. The frequency is in log units. The log axis is log. So this is again, the reason I'm showing you that this is often you'll see this kind of graph. So you can see the fact that there is a very nice flat response up to the cutoff frequency. And then from the cutoff frequency onward, there is a linear drop off. So this is that dB per octave kind of thing. What does that mean here in log units? That every time the frequency gets scaled by a certain factor, or let's say doubled, the loss will increase by a certain linear amount in log units, which is again in regular units means that it goes by a certain factor. So that's what this is now graphically visualizing the same aspect of that filter. This slope will be related to the order, exactly. So as we change, if we are able to change from second order to fourth order, you'll see that this part will just remain the same, and then you'll see this thing changing like that. Okay, so that's basically what I wanted to discuss about the filters. So we'll stop here and take a break. And then it's 12:15 now. So let's reconvene in 12:30 and I'll finish the last lecture by 1:30. Okay.